Okay, so this is 13.3, number 43, which highlights something I didn't teach you guys the other day. So let's figure it out. So I've got a vector v that's 3i plus 4j, and a vector f that's 0.2i minus 0.5j. And I'm supposed to calculate a, which is f parallel to v. Right? So that's the component of f that agrees with v. And then I'm supposed to calculate the component of f that is perpendicular to v. And then I'm supposed to calculate the work done, let's see, by the force F through displacement V. So work works the same way that you guys did work in Calc 2. Did you guys do Calc 2? Yeah. Sorry. Did you do work in Calc 2?
For a minute.
Okay, so what's a work? It's a force times a distance. Same thing in vector length. Take the force vector, multiply by the distance. Well, you don't really have multiplication, right? But you have dot products anyway. So you take an f and dot it with the vector v. That should be the easy one, so let's do that first. And take those and dot them, right? So you take your 0.2 comma minus 0.5 dotted with 3 comma 4 and get
0.6i minus 2j.
Wait, what?
Right? Isn't it?
Wait, what?
Yeah, wouldn't that be right?
No.
0.2 times.
So should be noted that I'm dismissing Ben's answer out of hand, not because it's particularly super wrong, but because it's the wrong category of object. So what category of thing do I expect this to be?
Oh, right. Oh my gosh.
Yeah, like this should be a number, right?
Yeah.
So anything with i's in it is definitely
Wrong. Yeah.
not it. But your numbers were correct.
Yeah.
So you get 0.6 and then
Plus minus 0.2.
minus minus 2. How about that? Multiplying, sorry. I have much more sympathy for multiplying wrong than writing down the wrong category. Not okay. Okay, so we got minus 1.4.
Yep.
What does that mean?
The
1.4
magnitude.
force in the opposite direction.
No.
They're going somewhere in the same direction.
They're good. They're obtuse.
So there's a force, right? Or sorry, a vector that I'm moving along and a force that's kind of happening. I got negative work out of that, right? Which means the force was pushing against me,
Yeah.
right? I had to put some work into this to move that thing. You guys see that?
So if work is negative, that means it's spontaneous, right? It means it moves by itself.
No, if work is positive, right? That's the work done by the
Yeah.
force.
Isn't anything you're pushing on pushing against you? Isn't that sort of like,
Is it dot product?
They could be pushing.
isn't that like the law of
with you.
physics?
Sorry, this is, did you get this for free or did you pay for it, right? If I drop this, right, the force field did the work,
Gravity.
right? So I got work out of the force field.
That'd be a positive reaction.
Yeah, that'd be a positive. Negative would be this.
You have to put 1.4 work into it.
Yeah, I had to put work into it to move it.
Okay.
Guys cool with that?
That gives us. It's like I thought for some reason didn't that give us like the theta for the cosine thing? Or?
Yeah, and you can, right, this was a dot product. You guys see that? So I found out that the angle was kind of obtuse-ish, right? You guys all see that? Like, there's a negative in there at least.
Yeah.
So that kind of means that there was something like this going. So the force field was pushing in the opposite, mostly in the opposite direction of the work I was trying to do.
What about if you push perpendicular to that force?
Yeah, you'll get nothing out of this.
Okay. Even though you're putting work into it? Like if you push the chair across the floor, gravity's going this way, you're not pushing against gravity.
Yeah, so if I move something across the table, right, that force field isn't doing anything to help or hinder me.
Yeah.
In this example, the force field is hindering me as I make this movement. You guys see that? Like,
Yeah.
the marker's on the table, it's perpendicular to gravity. Moving it doesn't cost me anything if there's no friction. Cool?
I just don't understand physics for
It's okay, neither do I.
Yeah, physics was canceled, so.
With work, you only consider the forces that are working either with or against or movement that you're taking into consideration. So you wouldn't count gravity if you're sliding the pen across the table because it's not working with or against the pen moving across the table.
Yeah, I just think that would work also, because I'm still expending energy to get something done.
If there's no friction on the tabletop, you don't need to
There
spend.
will always be in space.
Yeah, but we're.
Fair point, but idealized, right?
Yeah.
Yes. Okay, so now we need these two, the parallel component and the perpendicular component, which means I need to figure out how to project. Cool? So let me do this. Here's a vector u. Oh, okay. And here's a vector w. I need to first highlight what the heck I'm trying to do. So I would like to break w down into a piece that goes parallel to u. So I'm going to call that w parallel to u. And a piece that goes perpendicular, right? That would be w perpendicular to u. You guys want the easiest, dumbest example for this?
Sure.
Okay, so the easiest, dumbest example is that I and j thing that you guys are decomposing, right?
Okay.
So when you take a vector like 3, 4, and think about it as 3 i's and 4 j's, that's the parallel component to the x-axis and the perpendicular component to the x-axis.
Oh,
You guys see that? So we're just going to do that, but where we're not using the x-axis, we're going to use something else instead. You guys all good with this?
that only works because we're in 2 dimensions right now. Like if we jump to 3 dimensions, there's multiple perpendiculars. That doesn't exactly, it's not that simple.
Yeah, so in multiple dimensions, this gets a little funnier.
Yeah, okay, that's all I wanted to make sure of.
Yeah, you could still make projections onto vectors.
But it has to be of a plane, not of a,
No, you can still project onto one vector.
oh,
You'll get the parallel component, and then you'll get a perpendicular component that's just the shortest path.
okay.
It's still, there's still something there, it works all the way down, it's just weird.
Okay.
The pictures get harder to visualize. So let's do it here anyway. Okay, so I don't remember this formula either, so let's try to make it.
Yep.
First things first, thoughts? What am I going to probably start with?
Maybe find a couple.
Yeah, you probably find the angle. Yeah, that might help. At the very least, I should probably start with a dot product, right?
Okay.
You guys see
Yeah,
that?
'cause it's the cosine stuff. Yeah.
Okay, so let me think about what W dotted with U, right? Okay, but I'm going to try to break W into 2 pieces. So I'm going to say that's W parallel to U plus W perpendicular to U. And I'm going to dot that with U. You guys all good with that idea?
Yep.
Okay. Did I tell you dot products distribute like multiplication?
I believe it was in our book.
It is in your book. I can't remember whether I said that or not, but they do. So if I distribute this, what do I get? I get,
U W parallel to U and U W perpendicular to U.
okay, I get W parallel to U dotted with u plus w perpendicular to u dotted with u. And what? Good. So on the other hand here, right? On the other hand, this is mag w, mag u, cosine theta, right? You guys all with me on that?
Yeah.
Okay, so there's another thought that we might use lurking in the background, but right now I want to fiddle with this thing. So,
I have an issue I see, I don't understand. How is there a right angle there if all lengths of that triangle are W?
they're not. This is w parallel to u, so that's going to be some new vector that I'm going to make.
No. I was,
Okay, so which of these two pieces do I know about? I think I know about one of these pieces.
U.
Yeah, u is going to be a known quantity, right?
Yep.
So is w. How about this piece? What's special about w perpendicular to u?
Oh.
It's what to u?
Zero.
Yeah, w perpendicular to u is particularly perpendicular to u, right? So when you take w perpendicular to u and dot it with u, you're going to get 0, right? You guys see that? Okay. So this is going to be w parallel to u dotted with u. You guys all see that? With me, with me? Okay. And this business is going to be, what was that thing we were saying about magnitudes and cosines or some nonsense?
Oh, so magnitude of W, magnitude of U cosine theta is the same as magnitude of W parallel to U, magnitude of U cosine theta.
Okay, so this piece is, right, this is a dot product between two vectors. So this is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them, right? Uh-oh, I lost the thing I wanted. Where did I lose the thing I wanted? Oh, shit, that was dumb. I lost the thing I wanted. What am I looking for?
You're looking for
Yeah, so ultimately here I want to know something about W parallel to U, right? Okay, so let me think about that. What do I know about W parallel to U?
same angles.
It should be parallel to U, right?
Oh, so the cosine of theta for it will end up equaling 1.
Yeah, so that should be 1, right? You guys all see that? Okay, so here's what I know. I know that the magnitude of W parallel to U times the magnitude of U is equal to W dotted with U, right? If they give me two vectors, right, like we had over here, right, they're going to give me an F and a V, or a U and a W. And I'm trying to calculate these things. Well, so far what I can figure out is how friggin' long that thing is. You guys see that? So now you need to supply another piece of information here. What direction does W parallel U point me? Yeah, it's parallel to U, right? So this should be some number, right? Some scalar, times, let's see, if I put a u here, right, that would be enough. But now I don't know how long u is, right? You guys see that? So to keep track of how long u is, I might do this. First, what did I do? And second, am I allowed to do that? And third, why would that help? Okay, so I divided by the magnitude, which is a what category of object? Scalar. You know how to do scalar division, right? You don't know how to divide by a vector. So if I had forgotten the norm bars there, right, that would be bad news bears. But I can divide by a magnitude. So this piece, right, is a unit vector in the u direction. You guys all see that? And then this is going to be, no. Yeah, this is going to be the length of the parallel vector. You guys see that? So this guy really should be the magnitude of w parallel to u. And I know what that is. Well, I almost know what that is. You guys see it? Do you get it out of this? How do you get it out of this? Divide by what?
The magnitude of u.
Which you are allowed to do because it's a scalar. You guys see that's a little different than right here, where I could think about dividing by u, right? But this is a dot product with a vector, so you can't do that. But here, this is a scalar, so I can divide by that thing. So I think all told here, I get that w's parallel to u component is what?
W dot u
So w dotted with u
over the magnitude of u,
over the magnitude of u,
which ends up being the magnitude.
and then multiplied by u over the magnitude of u again. You guys see that? Which looks like a giant mass, and is a giant mass because I have two dots in here, right? What's this dot?
Dot product.
That is actually a dot product. And what is this other dot?
Multiplication.
It's not a cross multiply, it's not a dot product either. Yeah, that is literally scalar multiplication. You guys see why? Because all this crap, right, is a dot product which outputs a scalar divided by a scalar. So this whole deal here is a scalar. And then I'm multiplying that by a vector divided by a scalar. So there's two scalar multiplications going on there. You guys all cool with that?
Why did we multiply it by the unit vector?
To get it to point in the right direction. To make it a vector, right? Like, this whole deal is telling me how long this sucker is, and that's telling me which way it points. This is the classic direction and magnitude, right? You guys all see that? So over here, if I want F parallel to V, right, to go back to the problem I was originally doing, this should be what?
F dotted with v.
Okay, take the vectors, dot them together, divide by the magnitude of which one squared?
V.
Yeah, the one you're projecting onto. And then multiply by d. You guys see this? So I grouped this a little differently, right? I put all the scalars together and then the vector.
Should that be v to the, oh, magnitude squared, okay.
You guys all good with this? And you could do a little better than mag squared down here on the bottom. What's magnitude squared?
Just kind of thing dotted with itself.
Yeah, that's exactly the thing dotted with itself. So you can straighten this out a little bit, make it 2 dot products. That makes life a little easier, so you don't have to sort out which category of dot you're doing.
Why would it be a dot product? Isn't magnitude just a number?
Yeah, magnitude is a number. The place you can get the magnitude squared is you can dot a vector with itself. Or you could calculate the length using the Pythagorean theorem, right? The Pythagorean theorem in 17 dimensions sort of sucks, but dot producting a vector with itself is pretty easy, so. Okay, cool. You guys, let's see. So to get a number out of this, we get that dot product that we got before. So we got our minus 1.4 on the top, divided by, how long is the vector v?
5.
Yeah, that's a 3, 4, 5 triangle. So that would be 5 squared. And then I should be multiplying this whole scalar by the vector v, right? So that should be multiplied by the 0.34, or the, sorry, the what now? 3,4? Factor 3,4.
Wouldn't it be the unit version?
I took care of the unit version because I put the mag squared over here. You could certainly do the dot product over the magnitude multiplied by the unit vector, if that feels easy.
Less same, just squaring,
Yeah, square the components and add them together.
Okay.
So in the end, we're still getting I hat and J hat as well.
Yeah, so in the end here, yeah, this category of object will be a vector, right? And that'll be this one. So that's the component of this force that's parallel to V. And we can see that it's negative, right? It's pointing in the other direction. So this thing's not helping me if I try to move along this vector V using this force. This is swimming upstream. Maybe that's a better example. All right, how about F perpendicular to V? Okay, so I know this is going to seem tough, right? Because you don't want to go through that whole thing again. Good news, you don't have to. How do you get the perpendicular component?
Force vector minus.
Yeah. You guys see that? If I have W, right, and I have W parallel, what's special about W? Well, W parallel plus W perpendicular should be W, right? So to get the perpendicular one, you can just take the one you started with and subtract the parallel bit. So for F perpendicular to V, I'm going to take my vector F, right, my 0.2 comma minus 0.5, and I'm going to subtract whatever the heck you got here, that thing. You guys all see that? Okay, so the takeaway from this one maybe should be this formula for projecting. What's up?
I found a formula, it seems different from that, but it worked. It was magnitude of F vector times cosine theta of V over magnitude of V. I got the same answer, but there's no cosine theta in that, and I don't see where that would come from.
Good, perfect. Where's the cosine theta hidden in this thing? You guys all, does anybody see where the cosine of theta is hidden in here?
The dot product is one.
Yeah, it's literally part of that dot product, right? This dot product between W and U would be the magnitude of W, the magnitude of U, and the cosine of theta. And one of those magnitudes of U will cancel. So you'll get magnitude of W, cosine of the angle between them, times a unit vector pointing in the direction. Same thing. Usually it's hard to calculate that angle in between them without using the dot product. And so if you don't have to get all the way down to the angle, like, why? You guys see that? The cosine of the angle is really the important thing. It should be noted, right, that the result from a dot product, like this number, tells you roughly how much those two vectors agree. That kind of makes sense? Like in this case, I don't know, the magnitude of this thing's a little funky, but the negative sign tells me they're kind of opposite directions. If I knew how big they were, right, like this one's 5 long, this one's, I don't know, ballpark a little longer than a half or something, right? This number is quite a bit smaller than 5 times a half, right? So this is, they disagree, but they're not pointed in opposite directions. They're just kind of oblique to one another. You guys cool with that? That ballparking takes a little practice, but it's in there.